Hi everyone, I'll be talking about hardness of approximation for stochastic problems via interactive oracle proofs, and this is joint work with Alessandro Chiesa and Eylon Yogev. So in an interactive proof, or IP, we have a verifier who wants to know the validity of some claim. It interacts with the prover over multiple rounds, and then decides whether to accept or reject the claim based on this interaction. Completeness says that if the claim is true and everyone acts honestly, then the verifier should always accept. And soundness says that if the claim is false, then no matter what the prover does, the verifier should accept with probability at most 1/2. An interactive oracle proof, or IOP, is an IP where the verifier has local access to individual symbols of the transcript. This means that, rather than having to read the entire transcript, this means that the verifier can decide not to read some of the rounds, and the rounds that it does access, it can access just a few symbols, and decides whether to accept or reject based on this much more limited information about the transcript. A natural question when talking about interactive proofs is whether more rounds equals more power, and indeed Goldreich, Vathan, and Wigderson show that interactive proofs with k rounds are more powerful than interactive proofs with little o of k rounds. And we ask the question of what is the power of proofs with k rounds where the verifier only queries little o of k rounds or even bits. So there are many rounds of interaction, but the verifier doesn't read most of them. Our main theorem says that interactive proofs with k rounds can be transformed into IOPs with the same number of rounds, where the verifier queries at most k over log n bits. So notice that the verifier here doesn't query every round, doesn't even query most of the rounds. As a corollary of this theorem, we get that interactive proofs with log n rounds are decidable while querying just a constant number of bits. So there are log n rounds of interaction, but the verifier just reads a few bits, constant number of bits, and decides whether to accept or reject the claim based just on that. And well, when looking at this, the question is, can we get a constant number of bit queries for greater than log n rounds? Well, we don't know how to do this in general, but we do know for specific problems. So we show that any language that is interactively reducible with k predicates has an IOP with k rounds and a constant number of bit queries. And this interactively reducible property roughly says that the language has a k-round proof where transcripts can be merged together in some sense. And we show that k-variate Sumcheck is interactively reducible with k predicates, and that Shamir's protocol for p-space is interactively reducible with a polynomial number of predicates. And we also believe there are many more natural proofs that have this property. These are just the ones that we looked at. And as an immediate corollary of the theorem and these examples, we get that k-variate Sumcheck has an IOP with k rounds and constant number of bit queries, and then all of p-space can be decided using polynomial number of rounds, where the verifier reads a constant number of bits from the transcript. And this matches a result by Condon et al., although they looked at a slightly different model. An application of these results is for hardness of approximation. So in a constraint satisfaction problem, or CSP, we have a bunch of variables and a bunch of constraints of arity Q. And the value of the CSP is the maximum fraction of satisfied constraints when there's some assignment strategy that assigns values to these variables. The PCP theorem tells us that the value of CSPs with constant arity is NP hard to approximate to within a constant factor. A k-stochastic constraint satisfaction problem, or k-SCSP, is a generalization of a CSP, where the variables are split into two types, the R variables, the random variables, and A variables, which are existential variables. And the value is the maximum expected fraction of satisfied constraints when the assignment is chosen as follows. So first of all, R1 is chosen uniformly at random. It's also given to the assignment strategy, which then chooses A1 based on R1. Then R2 is chosen uniformly at random. The assignment strategy chooses A2, and so on, until all of the variables are given values. And we show that for every k, it is IP with k rounds hard to approximate the value of a k SCSP instance with arity k over log n to within a constant factor. So notice that if we plug in k equals log n here, we get constant arity. And previously, this was only known to hold for O of k, so we've managed to shave a log n factor from this arity. So let's get into the technical section. So we're going to show in this talk that interactive proofs how to take an interactive proof with log n rounds and transform it into an IOP with O of log n rounds and a constant number of bit queries. We'll do this in 2 steps. First, we'll take the IP and transform it into an IOP where the verifier queries a constant number of rounds, but it reads these rounds in their entirety. In the second step, we'll take this IOP with a constant number of round queries and transform it into one with a constant number of bit queries. This second step is done by applying a transformation from a previous paper of ours, which takes an IOP, transforms it into an IP, transforms it into an IOP, where the verifier makes binary queries, and with some minor modifications. And due to this, to the fact that this is from a previous paper, we're going to focus in this talk on step 1. So we want to take an IP with log n rounds and transform it into an IOP in which the verifier reads a constant number of rounds. Okay, so we have an interactive proof with k rounds. The verifier takes a look at the transcript after the interaction and checks whether it accepts or rejects this transcript. And we want to read a constant number of rounds from this interaction. So one idea is to have the prover send back the entire transcript to the verifier in one round at the end. Then the verifier simply needs to read this one round and then can decide whether to accept or reject based on reading one round. But of course, the verifier doesn't trust the prover to send the correct transcript, so it has to check that the real transcript, TR, is equal to the transcript sent by the prover, TR prime, and we want to do this locally by not reading the entire transcript, TR. So we're going to add a simple test. The verifier will choose some round index, and then check that TR and TR prime agree on this round. Okay, great. So let's analyze this protocol. First of all, notice the verifier is reading only 2 rounds, it's pairing just 2 rounds from the entire protocol. So we're doing great. We wanted to read a constant number of rounds. This is what we're achieving so far. Completeness is straightforward. If everyone acts honestly, there's no reason why this should fail. So let's take a look at soundness. There's 2 cases in which the prover can win and cause the verifier to accept. Either the transcript, the real transcript, causes the verifier to accept, in which case the prover doesn't need to lie while sending TR prime, it can just send the real transcript. But this happens with small probability due to the soundness error of the original interactive proof. The second case is if the actual transcript is rejecting, but then the prover has to send some TR prime that is accepting. This implies that the real transcript and the transcript sent by the prover disagree on at least one round. And the prover wins as long as the verifier doesn't query this specific round index in its check, which happens with probability 1 minus 1 over k. And so we end up with the verifier accepting with probability something like 1 minus 1 over k, which is really bad. We wanted a constant soundness error. So one could imagine doing parallel repetition, as we usually do to improve soundness error. We would need something like k separate executions to do this, to get constant soundness error. But unfortunately, each separate execution causes another query to the transcript, and this will increase the query complexity from constant, which we have now, to O of k, which defeats our purpose. We wanted to read a constant number of rounds, not O of k. So what do we do? Well, our main observation is the following. If the 2 transcripts, the real one and the one sent by the prover, disagree on more than 1/2 of the rounds, then the verifier accepts the probability at most 1/2, since it will find a round in which they differ with this probability. So we actually only need to handle the case in which the prover sends a transcript that is close to the real transcript, that agrees with the real transcript on at least 1/2 of the rounds. And this leads me to the following definition of robust soundness error. So an interactive proof has robust soundness error epsilon if the probability that there exists some transcript that is close to the real transcript and is accepting is at most epsilon. So, and I claim that this is enough to solve all our problems. And why is this? Well, we already claimed that if the two transcripts are far from each other, then the verifier will accept the probability at most 1/2. And if this property, if it holds, it says that if the two transcripts are close to each other, then the transcript TR prime is accepting with probability at most epsilon, which implies that the verifier accepts the probability at most epsilon, since it checks whether TR prime is accepting. So if we plugged in epsilon equals 1/2, we would be done. So our goal is to get this robust IP with error 1/2. And the idea is as follows. First of all, let's give ourselves a little bit of slack, add some more rounds. We now have 2k rounds rather than k rounds. And now the idea is that in any subset of k rounds, of these 2k rounds, will contain an independent execution of the original protocol. Why will this help us? So if two transcripts agree, the real transcript and the transcript sent by the prover will agree on 1/2 of the transcripts, it will agree on some k rounds, which will contain an independent execution of the original protocol, which will cause the verifier to accept. Let's take a closer look at this. So we have a k round interactive proof. We're extending it to 2k rounds, and the protocol looks as follows. For every set of the 2k rounds of size k, the prover and verifier interact on a separate session that works as follows. In the rounds corresponding to S, the parties run the original k round protocol, and in the other rounds they do nothing. So if you look at this example, at the beginning the prover and verifier do nothing, then they send the first round of interaction, then they skip a bunch of rounds, do the second round of interaction, and so on until they've done everything, and then they do nothing again. This is done for every set S. So here's an example of a different set S prime, in which they do something. They do the first round of interaction right at the beginning. They skip a lot of rounds. They do the second round of interaction while the previous session does its kth round of interaction, and so on. We do this for every different set S. And in the end, the verifier will accept if and only if in each of the sessions, the original protocol repeated over S is accepting. So let's analyze this. First of all, let's look at efficiency. So how many transcripts are there? Well, there's a transcript for each session. There's 2k choose k sessions because these are all the subsets of 2k of size k. And this is exponential in k. But remember, the number of rounds k is log n. So overall, this is poly n. So we're fine, even though we get this exponential growth. Now let's take a look at robust soundness. So our goal, remember, is that the probability that there exists some other transcript that is close to the real transcript and is accepting be at most 1/2. And now these transcripts that I'm talking about are the entire new protocol. Let's take a look at two transcripts which are close to each other. If they're close, if they agree on at least 1/2 of the rounds, then there exists some set S of size k, such that they agree on this session S. This is because there are 2k rounds and they agree on at least k of them. And then this, if we look at this session, the proof run during this session, then by soundness of the original protocol, the verifier accepts in this session with probability at most beta some soundness error of the original protocol. This is for every fixed S. So if we take a union bound over all sets S, we get that the verifier accepts the probability at most 2k choose k times beta, which can be made as small as 1/2 by doing parallel repetition initially for the interactive proof to get the soundness error to be very small. And then we're done. We get that if the transcripts are close, then the verifier accepts the probability at most 1/2. So we wanted to take an IP with log n rounds and transform it into an IOP with O of log n rounds and a constant number of bit queries. And so we started off by showing how to, we started wanting to get a constant number of round queries. We showed that we could do this, but it would would get very large soundness error. And then we showed that we could improve the soundness error if we used robust IPs rather than normal IPs. And then we took a detour to transform IPs into robust IPs. And once we get this IOP in which the verifier makes a constant number of round queries, we have the second step of transforming it into an IOP where the verifier makes a constant number of bit queries. And this was using transformation from a previous paper. So we're done. So now let's take a look at getting a constant number of bit queries for greater than log n rounds via interactive reducibility. So what was the problem that we had before? Why did we get stuck at log n rounds? Well, in the IP to robust IP transformation, we had a transcript for every subset of the 2k rounds of size k, and so the number of transcripts overall was exponential in k. So in order to handle greater than log n rounds, we would want to reduce the number of transcripts potentially to a polynomial in k. And our idea is to do this by merging transcripts together so that we have fewer transcripts overall. This merging property we call interactive reducibility. Works as follows. We have multiple transcripts of the same length, and we interactively reduce them into a single transcript such that if the probability that this new transcript ends up being an accepting transcript is approximately equal to the minimum of the probability that any of the original transcripts ends up being an accepting transcript. So notice that in particular, if all of the original transcripts are always accepting, then a new transcript is also always accepting. And if even one of the original transcripts is accepting only with small probability, then the new transcript ends up being accepting also with very small probability. And using this, we construct a variant of the IP to robust IP transformation, where the number of transcripts we have overall is poly k, and so we can handle any number of rounds. Previously, remember, we had exponential in k. Now let's look at an example of interactive reducibility for the Sumcheck protocol. In the Sumcheck protocol, we have a polynomial p of degree at most d over some field, and the claim is that the sum of this polynomial over the Boolean hypercube is equal to 0. In the ith round of Sumcheck, we look at the polynomial p prime, which is p where the first I variables of the polynomial are free, and the rest are summed over over the Boolean hypercube. Notice that the degree of p prime is also at most d. And we have an intermediate claim that p prime at some point r is equal to some field element gamma. And following the kth round of interaction, the claim is that the polynomial p at some fixed point r is equal to gamma, which can be efficiently verified by computing the polynomial at one single location. So now our goal is to take t intermediate Sumcheck claims and merge them together. Each claim is of the form p prime of r sub j is equal to gamma sub j. We'll first define two polynomials. The first polynomial, I, is a selection polynomial such that I of j is equal to r sub j for every j. And we can construct such a polynomial of degree at most t. Remember, t is the number of intermediate Sumcheck claims. We'll also define a polynomial g such that g of x is equal to p prime of I of x. So notice that by the definitions of g and I, we have that for every j, g of j is equal to p prime of r sub j. Also notice that the degree of the polynomial g is at most t times d, since the degree of I is at most t, and the degree of p prime is at most d. And now our goal is to use these polynomials to merge together intermediate Sumcheck claims. We'll do this as follows. The prover sends to the verifier a polynomial g tilde that is claimed to be equal to g. The verifier will check that g tilde of j is equal to gamma j for every j, and we'll choose a random field element f, rho. After doing that, it will output a new claim that p prime of I of rho is equal to g tilde of rho. Then let's analyze the probability that the verifier outputs a claim which is true. First of all, if all of the claims are correct, that is, for every j, p prime of r sub j is equal to gamma sub j, and g tilde is equal to g, then simply by opening up the definitions, we have that for every field element rho, p prime of I of rho is equal to g tilde of rho. And this means that if all of the claims are true, then the claim output by the verifier is true with probability 1. On the other hand, if even if one of the claims is false, that is, for some j, p prime bar sub j is not equal to gamma j, but g tilde of j is equal to gamma j, which must be the case because if the prover sends some g tilde for which this doesn't hold, the verifier rejects immediately. So if this is true, then this implies that p prime of I of x is not equal to g tilde. And so by the Schwarz-Zippel lemma, the probability over a random field element that p prime of I of rho, the random field element rho, that p prime of I of rho is equal to g tilde of rho is at most their degree, the degree of these polynomials, which is t times d, over the size of the field. And so this probability is a very small value. So this means that if even one of the claims is false, then the probability that the claim output by the verifier is true is very small. So just to summarize, we have that if all of the claims are true and the prover acts honestly, then the verifier outputs a true claim with probability 1. And if even one of the claims is false, then no matter what the prover does, the verifier outputs a true claim with very small probability. So using these ideas, and the ideas we've seen previously in the talk, we show that k-variate Sumcheck has an IOP with k rounds, in which the verifier makes a constant number of bit queries. And this extends to any language that is interactively reducible. And for the full definition of interactive reducibility, I'll refer you to the paper. And we still have open one major question, which is, can we take any interactive proof with k rounds and transform it into an IOP with the same number of rounds in which the verifier queries a constant number of bits, or does this only work for specific languages, such as those that have interactive reducibility? Right. Thank you for listening.